We are just moving on to the next presenter, who is José Arnoso. He's a senior scientist in the Institute of Geoscience, CSIC, and is a combined center between the Spanish National Research Council and the University Complutense of Madrid. And now he is the director of IGEO since October this year, so congratulations. You have a big effort now, just in this moment. His main research interests focus on geodesy and geodynamics using gravimetry, ground-based observations, and GNSS data to investigate surface deformation and gravity variations for volcanic monitoring. He develops mathematical models of volcanic processes with a particular focus on the Canary Islands, and also investigates earth tides and ocean tide loading for better understanding the elastic properties of the solid earth. So you are welcome. You have 20 minutes and a little bit more, and thank you very much.
Thank you very much for your kind...
This one, este es para avanzar y este es el puntero. Y pongo los 20 minutos y te aviso.
Okay. Buenos días. Thank you very much for your presentation. Good morning, everyone. So I move now to show you some results from our group regarding with gravity and geodetic, the analysis of gravity and geodetic data with regard to the eruption, the last eruption happened in El Hierro Island. I will not give you much details because it's very well known, the eruption, but the motivation for this presentation was not only the eruption of year 2011-2012, but only the 6 post-eruptive magmatic intrusions that did not produce another eruption. All these events produced seismicity, of course, ground deformation, and gravity changes, and produce a huge volume of magma emplacement in depth. So you see here, even the intruded volume in from the 6 post-eruptive intrusion is greater than the erupted volume. So what can we do with this in terms of the modeling of gravity changes and geodetic measurements? In El Hierro, our group started to make continuous gravity measurements in year 2008. It was very important because at that moment we tried to establish a base of knowledge in the island and installed a gravimeter in Aula de la Naturaleza in the southern rift of El Hierro. The analysis of this data, it was very important, as you will see later, in terms of the interpretation of the gravity effects during the eruption. But now, when the seismic unrest started in July 2011, the Spanish Geographical Institute installed a gravimeter to the north of the island because at that moment most of the seismicity was concentrated in this area. We can see a picture of the gravimeter installed there, and the meter was established there from August to September, because at that time the seismicity started to migrate to the south of the island. So the Spanish IGN decided to move the meter from Los Llanillos area in this place to our station in the Aula de la Naturaleza site. So, and during that time we have very important information, gravity information with regard to this eruptive process, as I will show you next. So, an example of the analysis of the gravity variations, in this case prior to the onset of the eruption. At that time, the gravity meter was installed there in the north of the island because the seismicity was concentrated here in this area. And this is an example of the gravity records. We can see the solid air tides variations. And in this square area, we can see a kind of jump that if we correct, make the appropriate corrections, correct the jump, they remove the solid air tides and so on. This is because it was important in our previous study in year 2011. We can obtain what we call the residual gravity. And we see that during these 2 days, we detect a variation of about 50 microgauss, which is huge. At that time, the seismicity was starting to migrate from the north to the south. So what can we learn from these gravity variations? This is the situation at that time. The seismicity starts to migrate. The gravimeter was installed here to the north. And we detect this gravity variation of about 406 microgauss. So we model this data in terms of a loss of mass produced by the magma drainage and density changes due to the fracturing produced by the migration of seismicity from the north to the south. So we were very lucky because only very few times you can detect any gravity change just in this moment when starts the migration of seismicity. So dikes intruding and so on. So what we do with this gravity variation is try to know what is producing these gravity effects in terms of modeling of gravity. Sorry. Okay. Oops. So we try to model these gravity variations in terms of a gravity decrease and also a density decrease produced by the effect that I mentioned you before. So it's very simple to compute the gravity change with this formula, and we suppose that at that moment we can model a vertical dike with 5 kilometers of vertical length and approximately 10 meters of width. With this, and because we have a previous knowledge of the subsurface structures of the island in terms of contrast density model made by our group, we can we make several tests and we detect, we model that for a density constant variation of about 250 kilograms per cubic meters and a depth of 12 kilometers to place the dike, we obtain a gravity change of about 25 microgauss, which is half of the observed gravity value. And then we model the density decrease in a similar way, but now using two hypotheses, one assuming a uniform density variation and another one from our previous model that I mentioned you before. In this case, with a density variation between 2,400 and 2,510 kilograms per cubic meter, we could explain a gravity change of about 20 microgauss. If we add to this other one, we have approximately about 45 microgauss of gravity decrease, which is what we observe with the meter in that position. Another interesting effect also observed with the gravity meter was this one, just the beginning of the eruption. If you remember, the eruption started on October 10. At that moment, the meter, as I mentioned you before, was moved from the north of the island to the Aula de la Naturaleza place in the south reef of El Hierro because of the migration of the seismicity. So when this is the signal, when start the eruption, the original data, we can see the solid air tides variation and so on. We can see some effects. For instance, this kind of gravity variation produced by the earthquake of magnitude 4.3, we produced the eruptive fissure. Here, if we remove the solid air tides and also the high frequency noise, which is a consequence of the tremor, of the volcanic tremor, we obtain these residual gravity variations, which is very, very interesting because during 3 days we have a very huge variation of gravity of about the first day of about 25 micrograms of decrease, and then it reaches about 100 micrograms. Then increase the gravity, decrease again during the first 3 days. At that moment, there is not practically ground deformation in the area around the gravity meter, so we must learn what is producing this gravity variation just in the moment of the eruption onset. Sorry, it's okay. There. So we focus on this gravity variation, but we know from the work from Martí and co-authors that during the first 3 days of the eruption, there was a migration of the eruptive focus northwards from about 3 kilometers in length, right? During 3 days. So we think that this is the gravity effect that we record with the gravity meter here, which is produced by a surface mass redistribution, right? So we can model also these gravity variations to see if it's coherent with this geological model. So this is the situation, our signal, and then again we make a direct modeling of this gravity change using the same procedure. But now because the eruptive focus was moving during the first 3 days to the north from about 3 kilometers in length, that means that the distance from our observation point, or gravity observation site to the volcanic focus is decreasing. So we were changed in the modeling, varying this distance, and then supposing a vertical dike of the same dimensions, we can compute the gravity variation, but now using our density contrast model. We place the dike in this area because this is an area where we have a density constant from high values and low, and with these constraints we introduce in the calculation, and we obtain for different thickness of the dike the different gravity variations between as we move from 12 kilometers to 10 kilometers of distance to the gravity station. We see the variation of gravity that can explain these variations during the first 3 days. So now continue with gravity, but now Hola? Sí. So we continue with gravimetry, but now in terms of time-lapse observations. In the island, we start to make, we develop a gravity network. In green color, you can see all the stations where we periodically make gravity measurements in order to study this kind of Sí. Vale. Bien. ¿No? ¿Se oye? Sí, sí, sí. Ok. Sí, sí, voy a pegar más. Well, so I show you some results concerning this gravity variation. We try to make as much as possible observations, more or less periodically. The last one was made this year. ¿Se va? Tengo que estar aquí pegadito. Ah, bien. Much better. Okay. Yes. We have a lot of measurements made during several years, but now we focus on this period of time because it's the period related with the eruptive event in El Hierro. Here. Of course, we compute the gravity variation from one year to another one, or from one survey to another one, in a least squares procedure, but it's involved a lot of corrections and so on. We must to remove the earth tides, topographic changes, groundwater effects, and so on. So, but I will move directly to the results. It's very complicated to this process, to explain all this process. And for instance, this is more important. This is the gravity difference between April 2008, before the eruption, and November 2011, 1 month after the eruption onset. We can see that there is gravity. Everything is sorry for that. Well, we can see that we have an increase of gravity to the north of the island. This is produced by the intrusion of new magmatic material from the upper mantle. In the center of the island, we detect gravity decrease produced by the magma movement toward the southern part of the island in this migration that I commented you before. And then to the south of the island, in the area of La Restinga, very close to the eruptive focus, we have a new increase of gravity produced by the magmatic material reaching the shallower crust, and also produced by the mass redistribution of the new topography by the submarine volcano. Okay. Another example is so I can show you this slide. We have gravity difference computed between year 2012, 15, and so on. And we can see that during this period, if you remember the eruptive and the seismic activity in El Hierro, during years 2012 and 2014, we detect a lot of seismic intrusions. Sorry, it's not serious. That produce if you remember, during these years, we have up to 6 post-eruptive intrusions, magmatic intrusions that very energetic, the seismicity indeed, but they did not produce any eruption, but place a lot of magma in depth. So, and this is the consequence in terms of gravity variation. You see a gravity increase in the northwest part of the island, mostly in the west rift of El Hierro, which corresponds to magma transport and storage during these post-eruptive intrusions. So it's very interesting in terms of gravity changes. Now I move to show you some results concerning the ground tilt measurements. In El Hierro, we also have a tiltmeter network. Tiltmeter is indeed detects gravity variation, but in terms of the orientation. Basically, it's a rotation of the ground, what is measured on this kind of instruments. We have several stations across the island. Usually, we install this kind of tiltmeters, which are biaxial electronic platform tiltmeters with different resolution, but in general, they are operating with 0.1 microradian of resolution. We have 3 basic or fundamental stations to the north of the island: Balneario, Aula de la Naturaleza, also used for gravimetry and also for GNSS, Montaña Quemada, and also we have 2 more stations that we use periodically in terms of if we need to to do some constraints and so on. Or, for instance, when we were studying the eruption in year 2011, and also to the west, in the west sector of the island, in the ESA site. But what is interesting is, in terms of the eruptive activity of year 2011, is what we record to the north of the island, in Balneario side, with this instrument, very small one, but very interesting. 1 month after the eruption onset in November, mid of November, we detect a tiltmeter signal, very strange. The meter is here. You can see the ocean time loading effect in the tiltmeter signal. This is the signal for both two components. One is orientated to the north and the other one in the east-west direction, right? This is our usual configuration. And indeed, I arrived to El Hierro in November 11. At that time, it was started a kind of reactivation of the seismic activity, more energetic. And when I see this signal, I was thinking that the instrument was broken, some electronic problem and so on. But I decided to, okay, I will keep it because but I don't like this signal. But indeed, in November 12, I come again to the station and disconnect and then reconnect again. But when we analyze in more details this signal, we indeed see that this kind of tilt variation was related with the seismic activity at that time concentrated in the north. This is the seismic signal in the north. We use the seismic information from Spanish Geographical Institute. This is the relocated earthquakes for these days between 7 November and 14. And this is our signal. Also, we have to take into account the geological model at this moment from the work of Martí and co-authors. This is a schematic representation of this model. Two magma chambers connected with a vertical conduit to the north of the island. Over here we can see two different depths. One chamber is about 20-25 kilometers. The other one between 10-15 to approximately to the Moho depth. Okay, and this is the diagram of this geological model. So we think that this is connected with our signal observed here. So if you see, we have in this signal a variation of about 40 microradians, a kind of long-term variation, but also a high-frequency signal, which is in terms of... thank you so much. Hola, sí. In terms of, we have the long-term signal, and also this strange signal is produced by kind of cyclic tilt variation, right? With peak-to-peak period of about 4-5 hours, but only during 3 days, and only recorded in this station. In the other tiltmeter station, we have not this kind of signal. Indeed, in this, okay, I will comment you later. Okay, I will try to go faster. Is it because of the flight? It does not work. The pointer, I cannot change the slide. No. Ahora? Now it's going. Yeah, okay, thank you. So what we obtain, we can obtain, we try to obtain as much as information from this cyclic signal. To do so, we use the singular spectrum analysis. I will not go into details of this method, it's very well known. But what we do with this analysis method is try to extract common patterns like nonlinear trends, cyclic signals, and so on. This is a kind of flux diagram of the singular spectrum procedure. So we try to extract from the original signal the dominant spatiotemporal patterns and to reconstruct the signal in terms of principal components, and then use the Monte Carlo approach to discern if the singular spectra is a real cyclic signal or random noise. So we extract this kind of signals using this procedure. Now again, is blocked this. Ahora. As a result of this procedure, you have on the left the singular spectrum for 20 eigenvalues detected with this method, and in the right the same values. And you see that the components 1, 2, 4, and 6 except the 95% confidence intervals. So we can link these principal components to a real tilt signal. These are the 4 components, these are the long term, and these are the cyclic tilt signals for component 2, 4, and 6. With these principal components, we can reconstruct the original tilt meter signal for both components. In red color is the reconstructed signal with these components, and in blue is the original one. So we extract with this method the information which is of interest in terms of these cyclic tilt signals. And now we try to find what causes these cyclic signals. To do so, we have this situation. This is the results of the reconstructed tilt meter series with the components, the cyclic components 2, 4, and 6. And this is the geological model, the 2 magmatic chambers connected with a vertical conduit, and so on. So we try to use this information, our reconstructed signal and this geological model, to introduce in a physical model in this way. We have the magma ascent from the lower to the upper reservoir. You have a crystallization produced by the compression, which increases the viscosity. So this slows the magma flow and causes that pressure built in the upper magma chamber. When a threshold is reached, the magma velocity increases, and if this cycle is repeated, we have a kind of pressure pulse in oscillatory pressure pulse. That produce ground deformation in the surface, right? So this is the observed pulses, and this is the modeled one with this physical model. And we see that for in several cases we can show a positive correlation between them for periods of 5.3 hours. So this system is governed by pressure dynamics and viscosity change that affect the magma flow and generate cyclic pressure pulses that produce these tilt signals detected on the surface. And just to finish, sorry for my delay, some comments regarding GNS analysis of GNS data. We have several stations in the island, and we use also, information from public places, not much, from public sites, from GrafCam, Spanish IGN, this is our station, but we also use non-permanent observation in several places in order to make surveys, different surveys along the years, right? But not to compute itself variation of coordinates. In our case, what are we doing is computing the GNSS strain, because give us information regarding the deformation in the surface. We use episodic surveys to compute the velocities, the difference of coordinates between one epoch to another one, and also observation from permanent sites to compute the velocities. But in this case, because we have long-term series, we need to proceed to make a least square procedure in order to remove periodic components. So we compute the strain tensor in this way. We compute elongations, principal strains, and the areal strain, the dilatation, the deformation in the surface. I show you very fast several examples of the areal strain for the periods between year 2015, 17, 18, and you see there is a compression in the northwest sector of the island, the western reef of the island, which is changing its magnitude along the years, and also some dilatation, mostly in the central and east sectors of the island, which is like also varying in magnitude along the years. And on the right, we have the maximum shear strain, which present a shape in accordance with the areal strain, with maximum shear strains in the west sector of the island. Right? Also, we can do a similar calculation now using continuous GNSS observations, but because the information from this station starts for year 2019, this is an example of the difference between year 2021 and 2019. We found a slight subsidence of about 3 millimeters per year in the 4 stations, and we compute also the areal strain for this period. We see that this the pattern is slightly different from previous calculation of the other years, and also lower in magnitude, right? So, just to conclude, I show you several examples of analysis of gravity data. Gravimetry is very important. I think it's essential, and mainly in these cases of the eruptive process that we cannot see anything because it was submarine. But the gravimeter observations in the surface give us a lot of information. So I think it's essential for tracking the magma dynamics in this kind of process. Also, the tiltmeter networks are a very valuable technique for modeling these changes in the magmatic process. And as we can see in this example that I showed you, the dynamics of the magmatic plumbing system in the eruption of Tagoro volcano. And also, I show you very fast several results concerning the GNSS strain field, which is show that is very influenced by the post-eruptive intrusions during years 2012 and 14, which is compatible with magma accumulation and magma displacement in depth during these years. So gravimetry, ground-based and space-based geodetic techniques are very useful and crucial, in my opinion, for understanding this kind of dynamics of submarine volcanic events, as in the case of Tagoro volcano. Okay, thank you very much, and sorry for the inconvenience.